an inverting amplifier in which a input sine wave 2.4 sine 2000 pi t is applied. So our V input is equal to 2.4, peak value is 2.4 volt sine 2000 pi t. So frequency is equal to 1000 hertz, that is 1 kilohertz. Being 2 pi f equal to 2000 pi, so frequency is 1 kilohertz. Time period is 1 by f, that is 1 millisecond. So time period is 1 millisecond. So t by 2 is 0.5 millisecond. Now R2 by R1, inverting amplifier gain is minus R2 by R1 is equal to minus 10. So output will be 10 times, that is 24. The output will be 24 sine 2000 pi t. But it will be chopped at plus 12 or minus 12 volt. So we have to find out the time t1 at which it will be chopped at minus 12 volt. So the output is minus 24 like this. So let at t1 the output is minus 12, so it is minus 24 sine 2000 pi t1 gives t1 is equal to 1 by 12 millisecond is equal to 0.083 millisecond. Here it is t1 is equal to 0.083 millisecond. Because 12 by 24 is 0.5, 0.5 means sine pi by 6, so 2000 pi t1 is equal to 2000 pi t1 is equal to pi by 6. It cancels out, giving t1 is equal to 1 by 12,000, that is 1 by 12, this is second, this is millisecond. 1 by 12 means 0.083 millisecond. From this output, from the symmetry of the graph, T2 will be 0.5 minus 0.083, that is 0.417. Let us check it. At this value, if we put T2, we say T2, then this is, we have told you 0.417, 0.5 minus 0.083 minus 0.5 minus 0.083, so it is 0.4. T2 equal to 0.417 millisecond. Let us check it. The value of V output at that very time. V output is equal to minus 24 sine 2000 pi, say it is T2. So it is minus 24 sine 2000 pi, T2 means 0.417 millisecond. So it gives sine 0.834 pi, which is 0.498, giving minus 11.9 volt. This is the value, almost minus 12. So it is checked. Similarly, from symmetry we get this value is 0.5 plus 0.083, that is T3 is equal to 0.583 millisecond. This value is 0.583 millisecond. We can check it in similar way. If we call this time T3, then it is nothing but T3, and it is minus 24 into sine 2000 pi. T3 means 0.583, which gives millisecond, that is 10 to the power minus 3, giving minus 0.498 minus 24 into this, giving plus 11.95 volt. So it is again 11.9 volt, that is plus 12 volt. Similarly, this is 1 millisecond minus 0.083, this is T4. T4. This time is T4. T4 is equal to 1 millisecond minus 0.083 millisecond. That's equal to 0.917 millisecond. Let us check it. Sine minus 24, the output is equal to minus 24 sine 2000 pi into 0.917 into 10 to the power minus 3, giving minus 24 into minus 0.498, that is again almost 12 volt. Let us examine the situation experimentally. This is the OPAM 741 IC. This is the number 2 pin is inverting terminal. Number 3 pin is non-inverting terminal. Pin 4 is connected to minus 12 volt. Pin 7 is connected to plus 12 volt, and pin number 6 is connected to output. So pin number 7 is connected to plus 12 volt and pin number 4 is connected to minus 12 volt. This is a breadboard. The points in this position are connected in this fashion in the column wise. The points in this position are connected in row wise. There is a gap between this, so that the pins of 1, 2, 3, 4 and pins 5, 6, 7, 8 are not short circuited due to this gap. Look, the pin number 2 and 6, in between these 2 points there is a resistance 10K, and this is the resistance from 2, and the input point a resistance 1K. Note that there is a dot in this position. This is the pin number 1. So this is pin 2, this is pin 3, this is pin 4, this is pin 5, 6, 7 and 8. We have a resistance between pin number 2 and the input. So our input point is this. We will apply a function generator at this point. This resistance, which we have already connected just now, is nothing but a 1K. So between the point 2 and the point 6, pin number 6 is 4, 5, 6. This is 10K resistance. So our ratio is minus R2 by R1 is 10. Now we have to connect pin 4 to minus 12. This will go to minus 12. Pin 7 will go to plus 12. So this wire will go to plus 12. Pin 3, this one, will go to ground. Let us suppose these are ground line. So let us connect these to ground position. And now we have to take output from pin 6. So this is our output. We will again go to the CR. This is the circuit of an inverting amplifier in which there is a resistance of 10K between the point 2 and the point 6, pin point 2 and pin point 6. And there is a resistance 1K, which is input resistance between pin point 2 and the input point. Input is in this way. This is the function generator. This is the positive terminal of the function generator, and this is the positive terminal of the channel of CRO. Look, this is the pin 2 and this is the pin 3. Pin 3 is connected by this wire to the ground point. So this is just a inverting amplifier. Pin 7 is connected to power supply plus 12 volt. Pin 4 is connected to minus 12 volt, and which is shown in my next slide. This is plus 12 volt goes to 7, pin number 7. This is minus 12 volt, goes to pin number 4, and this is ground point is connected in this position so that all these points are grounded. These are the grounds from function generator and CRO, etc. And output is taken from the point 6. All this output and input are fed to CRO. This is the CRO. Look, time per division is 0.5 millisecond. Time per division is set at 0.5 millisecond. So, bigger divisions are 0.5 millisecond per division. There are 5 divisions within big 2 divisions. So, one small scale division is 0.5 by 5 is equal to 0.1 millisecond. Note that it is millisecond. Similarly, channel 2, this is channel 2, is set at 2 volts per division. So, one small scale division is 2 by 5 volts per division as before. This is channel 1 which is set at 5 volt per division. So, bigger divisions are 5 volt per division and one smaller scale division is naturally 5 by 5 equal to 1 volts per division. Now, look at the output and input. This is my input and this is output. Look, in output there are both in the input and output there is 5, 1, 2, 3, 4, 5. 5 smallest divisions are there. So, these are the bigger divisions and these are the small scale divisions. Similarly, in time scale also, this is 1, 2, 3, 4, 5. There are 5 smallest divisions in between a bigger division. This is 0.5 millisecond, so all these are 0.1 millisecond. Now, this is a complete cycle, so time period is 0.5 and 0.5, that is 1 millisecond, so frequency is 1000 Hz, that is 1 kilohertz. Now look at the peak to peak value. Here it is 5, 10 and almost 13 or 14 divisions. Let it 13 divisions. 13 into 2 by 5, this is 5, this is set at 2 volts per division, this is 2 volt. So, one smallest division is 2 by 5. So, 13 into 2 by 5 is equal to 5.2 volt. So, peak to peak value is 5.2 volt and peak value is 2.6 volt. This is the input, peak value is 2.6 volt. Now, look at output. This is set at 5 volts. The bigger division of channel 1 is 5 volt per division. So, one small scale division is 5 by 5 is equal to 1 volt per division. There are 18 divisions almost, 18 or 20, look like 5, 10, 15, it is almost 18, 19, so it is 20. So, 20 divisions and it is set at 5 volts per division, or small scale division is 1 volt. So, it is 20 volt, almost 20 volt peak to peak value, giving peak value is 10 volt. So, it is sharply chalked at 10 volt, that is it goes to saturation. Plus Vsat is 10 volt, say minus Vsat is minus 10 volt, then peak to peak is almost 20 volt. So, it is chalked at its saturation value. This is the complete picture of the CRO. This is our input, this is our output, this is time per division, this is channel 2, this is channel 1. Channel 1 is set at 5 volts per division, channel 2 is set at 2 volts per division.